All right, hi everybody. Welcome back to Math Background for ML. So last time around we were talking about preconditioning and momentum. So as a reminder, this is about the problem of how to do optimization, right? So you've been using stochastic gradient descent to do a whole bunch of different optimizations. And stochastic gradient descent is great, but occasionally it converges really slowly, and the usual reason for that, or one of the most usual reasons, is poor conditioning. And so we defined the condition number of a problem, right, which is if you take the singular value decomposition of the Hessian, right, so if this is our Hessian matrix, then right, you take the matrix of singular values and you take the ratio of the largest to smallest. That's the condition number. A good condition number near 1 means that the contours of our loss function that we're optimizing are close to circular. And a bad condition number, meaning a really large one, you have long skinny contours. And with long skinny contours, gradient descent tends to get stuck jumping back and forth across the contours and not making, across the short contour and not making much progress along the long one. All right, so we were just going to, if I remember right, start talking about preconditioning. So the question that we want to answer is, suppose that we didn't need to worry about computation, what would be the best possible way to make the condition number of our problem better? And so it turns out that there's a way to make it perfect, at least locally, and that is to do a change of variables. So if we have our original variable w, and we factor our second derivative matrix. So we have our matrix H, that's equal to the second derivative of our loss, and we set, we factor H is equal to A times A transpose, right? So otherwise known as, I'll write it in quotes, A is equal to the square root of H, right? That's not the same square root that you're used to with ordinary numbers, but it basically means if you multiply A by itself, you get the second derivative matrix. So if you do that, and then you take a new variable v and you set it equal to A inverse w. W was our original variable. And if you do a change of variables, our loss function was at least locally w transpose hw. And if you substitute av, which is the same as w, and do a little bit of simplification, then you get that our loss function is locally just v transpose v, meaning that the second derivative matrix is the identity. The identity has all singular values equal to 1, and so the condition number, the ratio of the largest to the smallest, is 1. It's got perfectly circular contours. And so that's great. If we knew the Hessian and could afford to factor it, then everything would be good. But often computing the Hessian is expensive, and factoring it can be even more expensive, and so we can't afford to do that. But what it suggests is that what we should do is make a change of variables with something near the square root of the Hessian, some simpler approximation to the square root of the Hessian. And so to do that, right, so that strategy is called preconditioning, just doing a change of variables with a matrix that's supposed to be somehow near the Hessian. And one of the simplest ones is a diagonal preconditioner. You basically take the diagonal entries of the second derivative matrix, which is to say the second derivative with respect to each variable. We don't look at all at cross second derivatives. And so this is obviously losing some information because you know, the off-diagonal elements of the second derivative matrix, they mean something, right? They tell you something about how the variables interact with one another, but at the very least, if you can, you know, it's much faster to work with only the diagonal elements, right? There's order d of those in d dimensions, or order square root, or order d squared of the full matrix, and so it's much better to use, much more efficient to use just the diagonal entries. All right. So, so there are tons of other ways to do preconditioning. Some that you might have heard of are Adagrad, incomplete Koleski factorization, BFGS, which is short for Broyden, Fletcher, Goldfarb, and Shano, and natural gradients. And so we're not going to have time to cover all of these there. There are entire courses that you can take on optimization, but if you happen to run into a very poorly conditioned problem, it's worth Googling those terms and looking to see if any of them will satisfy, you know, will help you improve the performance. There is one method that helps with conditioning that is really simple and really common, and that's momentum. And so I did want to talk about that just because it's a nice and easy trick that you can use. All right, so let's take a look in a little bit more detail at what's going to happen. So let's say that we've got two vectors, right, in our maybe I'll draw it here, right? So we have our space, and we have the contours of our loss function. So our loss function, let's say that the contours look like this, right? Narrow along this direction, and wide along that direction, right? And so we'll call this direction U1 and this direction UN, right? Because this corresponds to the largest singular value of the Hessian, and this corresponds to the smallest one. And obviously I can't draw, you know, a 27-dimensional loss function, but there's going to be a whole bunch of other dimensions that have properties in between these, but we don't have to worry about those. We can simplify the picture and just look at the first and the last. And so the gradient of our loss function is going to tend to be small if you project it onto this direction, and large if you project it onto this direction. And so if you set a learning rate, you'll tend to take giant steps in this direction and tiny steps in that direction. All right. So what we would really like to do is set different learning rates in the directions U1 and UN, but the problem is we don't know directions U1 and UN to start off with. And so, so we can't do that. But what momentum does is it gets more or less the same effect without having to worry about it. And so the way it does that is it distinguishes between these two directions using properties of the gradient updates themselves, right? So what I said before is that along the UN direction, right, we're going to have a small gradient, but it's going to be like, since we're not moving, it's going to keep pointing always more or less in the same direction. It's just going to be too small. Whereas with u1, since we step back and forth, right, our gradients are flipping directions, but they're bigger. And so what we're going to do is we're going to do sort of a low-pass filter on our gradient. We're going to average them together over a window of iterations. And so if there's a direction that the gradients are flipping back and forth a lot, they'll tend to average out and we'll get a small average gradient. And if there's a gradient that they always tend to keep pointing in the same direction, they're going to reinforce each other and point in that direction without getting smaller. And so what that's going to do, if we use this averaged gradient, it's going to cause us to make faster progress in any direction where our gradients are consistent, and it's going to slow down our progress in any direction where our gradients are inconsistent. So how do we do that explicitly? Well, here is the update. What we do is we have our gradient g, and we'll keep a vector h, which is the average gradient, and we just, on every iteration, take theta times h plus 1 minus theta times g, right? So theta you can think of as being a number close to 1, and so if you take 99% of h and 1% of g, that's going to sort of keep track of gradients over the last 100 or so iterations, and sort of average them together. And then we do the gradient descent update with h instead of with g, right? And so g can be either the true gradient or it can be a stochastic gradient estimate, just like in ordinary SGB. And the reason this is called momentum is that if you think about how it's going, right? You have the direction you're going. Like once you build up speed in a given direction, you tend to keep going in that direction, and so it's like physical momentum. It's not precisely physical momentum, but it is it's a metaphor, and so that's why we have that name. And momentum and preconditioning, these are two orthogonal things you can do. You can do one or the other or both or neither, and their effects tend to be cumulative. So if you precondition and use momentum, you'll get the best of both worlds if you can come up with a good, inexpensive preconditioner. And momentum's always cheap, so it's almost always worth trying. All right, so that's everything I wanted to say about unconstrained optimization. So the sort of recipe that works pretty decently well most of the time is to run stochastic gradient descent with momentum and with the best preconditioner that we can compute at a reasonable cost. That doesn't always work, but it's a good place to start. It's sort of the jackknife of optimization methods. It's not the best tool for anything, but it's the second best tool for a lot of things. And so, yeah, there are fancier versions as well. So if you've heard of Atom, which is a really popular optimization method for deep neural networks, it's basically a diagonal preconditioner plus momentum on top of stochastic gradient descent. And so that tends to be quite successful in optimizing deep nets, and it uses basically the tricks that we've been discussing. All right. So if people have any questions, feel free to ask them on Piazza. And I'm going to next move to constrained optimization. But before we do that, I think between sets of notes is a good time for a quiz. So let me go ahead and put one up for everybody to work on. All right, so the quiz is now released on Canvas. I'll post it on Piazza as well. We'll pause the stream for a little while, and I'll be back in a few minutes. for everybody to answer questions and or keep going on the next set of lecture notes. So yeah, so work on the quiz, and I'll see you in a few minutes. All right, everybody, we're back. If you would like to keep working on the quiz, please just pause me. But enough people have made enough progress on the quiz that I think it's probably worth coming back and looking at the next set of lecture notes. There was an interesting question on Piazza while we were on the break, so I figured I'd answer that here as well. The question was how to interpret a precision matrix. And so there's a couple of ways to do this. One is just to say, well, don't interpret the precision matrix, take its inverse and interpret the covariance matrix. That's maybe not all that helpful, but you can fall back on that if nothing else works. The other is that the entries of the precision matrix tell you how much direct dependence there is between two random variables. So if let's say that you have a random variable x and a random variable y, and the xy entry of the joint precision matrix is small, that means that a change in x is not directly associated with any change in y. All of the change is mediated through other variables. Whereas a large value means that if you change x, you would expect y to change a lot. And there might be additional changes that are mediated through other variables. Oops. So it looks like our video is frozen again. I need to figure out how to get that to stop happening. We'll just all right, here I am back again, non-frozen. All right, so the entries in the precision matrix correspond to how much direct statistical dependence there is between variables. And then the last way to try and interpret the precision is if you look at the singular value decomposition of the precision. So you'll get a whole bunch of directions. And the directions that correspond to large singular values are directions where you very precisely know your position. So that's sort of high precision. So in other words, you're going to be very close to the mean of the distribution in the directions where you have high precision. And in the directions where you have low precision, so you have a small singular value in some direction, you're going to have a lot of variability around the mean in those directions. So that's how to interpret a precision matrix. All right, so let's look now at constrained optimization and a related topic, which is optimizing non-smooth functions. So far we've used SGD to solve unconstrained problems, right? They look like this one, where we have a sum of terms, L0 plus the sum of LT of W. And so we'd also like to be able to solve problems that look like minimizing the same sort of loss function, but subject to the constraint that W has to lie in some set C. Related to that, right, so we've been using stochastic gradient descent, which implies that the loss functions are differentiable. And if we have loss functions that are not differentiable everywhere, we would like to be able to handle those as well. This is not just a theoretical problem. This sort of loss function happens all over the place in machine learning. So a few common examples are lasso, which is a variable selection method based on penalizing the L1 norm of your weight vector. Support vector machines, which are a constrained optimization. They're basically like perceptrons. They're a linear classifier, but they're looking to optimize the margin of classification. So margin means this, right? We have a whole bunch of positive examples and a whole bunch of negative examples, and if we're able to separate them by a plane that has a bunch of room on either side, that's called a high margin. And so there's some theoretical reasons to believe that high margins correspond with good generalization performance, and so support vector machines try to find that, and they're a constrained optimization problem. And then non-negative least squares is another good example. This is linear regression, except that you constrain some of the coefficients to be non-negative, which means that you have a monotone increasing relationship between some of the inputs and your output. All right, so that's just some examples. What are our options for solving constrained optimization problems? So maybe the simplest one is what's called projected stochastic gradient descent, which is just like ordinary stochastic gradient descent, except that after every iteration, we project onto our constraint set. So, you know, for example, if we have a constraint set that looks like this, and you know, let's say we're here and we take a step out to there, we would project back then, and our next iterate would be there. Projection just means minimizing the Euclidean distance subject to remaining in the constraint set. So the algorithm looks like this, right, where pi, capital Pi, is the operation of projection. So you take an ordinary SGD step and then project back onto your constraint set. And just like stochastic gradient descent, it's a good idea to use preconditioning, decreasing learning rates, early stopping, mini batches, all of the other tricks that we've been talking about. So mini batches in particular work well with projected SGD because in case your projection operation is at all expensive, you only have to do it after the end of every mini batch. And so you get to spend more of your time with mini batches. You spend more of your time computing gradients compared to the amount of time you spend projecting. Now, projected SGD is only a good idea if we can project really efficiently, because we're doing a lot of projection operations. So an example of that would be where we have a box constraint, just upper and lower bounds on each one of our variables. The way you project there is for each variable independently. If it's above your upper bound, you move it down, and if it's below your lower bound, you move it up. And obviously that's pretty efficient, and so you can afford to use it in projected SGD. Now, projected SGD doesn't work, or it works but really slowly, if you have a more complicated constraint set. And so we'll get later on in this set of lecture notes, we'll talk about ways to handle more complicated constraint sets. Before we get there, it's worth talking about how to handle non-smooth terms, meaning non-smooth terms are terms L sub t where the gradient of L sub t doesn't exist everywhere, doesn't exist at all possible values of W. Now, as with many problems, maybe the most common way to handle it is to ignore it. And so you can often do that. So if you have a non-smooth term that looks like this, right? So here is W dot AT is increasing in that direction, and if you have a loss term that looks like this, right, which is trying to encourage W dot AT to be bigger than or equal to this cutoff, which we can say is equal to 1. So that's useful in classifiers like a perceptron, like you're trying to get the dot product between W and A to have a positive sign. Okay, so if you have a term like that, you can differentiate it almost everywhere. And so what you'll do is just run stochastic gradient descent and say, hope that you don't hit a place where you can't compute the gradient. And actually, it's fine if you do, right? There's sort of two gradients at this point, right? There's the gradient on the left side and the gradient on the right side. And so if you hit that point, you're actually fine. You can use either one of those gradients. And so that doesn't, that sounds like a horrible hack, and maybe it is, but in fact, it's guaranteed to work in some circumstances. So for example, for convex minimization, it doesn't matter if your loss terms are not differentiable everywhere, so long as they're convex. However, the conditions for convergence are definitely more subtle than they are for smooth loss functions, and so it's worth thinking twice when you use SGD on a not differentiable problem, because any problems in convergence could potentially be attributed to the behavior of the loss function around one of these points of non-differentiability. The other thing is that one of the things you can do is have a loss function, right? So if you have a loss function for some component of W that has a point of non-differentiability at 0, what you'd like is for, right, if you have a non-differentiable minimum at 0, what you'd like is to have your loss function, you'd like to have it stick at 0, right, like at a hard 0, so that you have an actual sparse weight vector. And SGD is never going to achieve that. It'll just step back and forth across 0. It might get really close to 0, but it won't be a hard 0, and you'll never have a have a hard sparse loss vector. Parameter vector. And so for both of these reasons, we can try and handle non-smooth terms and constraints in slightly smarter ways. And one of these slightly smarter ways is what's called proximal stochastic gradient. And proximal SGD can actually handle both constraints and non-smooth terms. So it's a strict generalization of projected SGD. So it's for problems of the standard form where L0 is not necessarily smooth, and it might actually incorporate a constraint. So how can we incorporate a constraint into a loss function? Right? So if we have a loss function which looks like this, right? So it's the loss function between -1 and +1 is equal to 0. And then it goes up to infinity immediately when you cross either of those. Well, that's equivalent to having a constraint, right? Because if your loss function is infinite, you're going to say, well, no, I don't want to go there, and you're just going to find a point that satisfies the constraint. Now, not all methods can handle loss functions that are infinite, but proximal SGD can handle it specifically if L0 is infinite in some places. All right. So proximal SGD is based on a minimization problem that looks like this. So we'll call it the proximal operator for a function f, which is to minimize square difference between your old weight vector and your new one plus f of your new weight vector. And so this is kind of a weird looking operator, the prox operator is, but one way to interpret it is that you can see it's a generalization of projection. So in particular, if you set your function to look like this, where it's infinite outside of your constraint and 0 inside your constraint, then minimizing distance plus f is basically saying, well, f is either 0 or infinite, so you take a place where f is 0, and then you minimize distance. So it's equivalent to saying minimize distance subject to being in this constraint set. So it's exactly equivalent to projection in that case. So, however, there are, we'll see later an example where we use a more complicated prox operator. All right, and so proximal SGD repeatedly takes a gradient step. So it replaces W by W minus eta times a gradient estimate. Again, that could be an ordinary gradient or a stochastic gradient estimate. And then applies a prox operator to the result instead of a projection like projected SGD. So okay, so you can see that prox SGD generalizes ordinary SGD. And so, again, it inherits a lot of the properties. It's a good idea to use preconditioning, mini batches, all of that sort of stuff. In particular, again, mini batches can save a lot of computation because we're doing the prox operator a lot, once after every iteration. And so we would like to, A, have a very efficient prox operator if we can, and B, do a whole bunch of gradients per iteration so that we can spend more of our time computing gradients and less computing the prox operator. So prox SGD, sorry, there's a question on Piazza. How might we go about finding the conditional expectation from the precision matrix? That's actually in our notes on Gaussian graphical models. There are specific directions for finding a conditional distribution in a Gaussian graphical model, and that takes as input the mean vector and precision matrix. And then in that conditional distribution, there'll be a mean, and that will be the conditional mean. So, right. So back to proximal SGD. Let's do an example. So the example is going to be lasso. And so in lasso, it's going to be a linear regression problem. So we're going to minimize squared error, the sum over all training examples of y minus w dot x squared. But then we'll penalize a multiple of the one norm of w, right? So this is the one norm in one dimension, and you can see it's encouraging the weight vector to be 0, not forcing it, but encouraging it. And in many dimensions, the one norm basically encourages all of the components to be 0, and then only the ones that have sufficient incentive to move away from 0 will do so. All right, so lasso accomplishes variable selection by setting some of the components of our weight vector to a hard 0. So with a little bit of math that I won't go through, you can derive the prox operator. It basically says, okay, so the gradient of this penalty term says to move w towards 0. And what the prox operator does is it will it will move w towards 0 and then have it stick there. So it'll you know, if you're over here, you'll just, you know, if w is over here, you'll move a little bit that way, and if w is close here, you'll move exactly to the origin and stick there. And you know, that's I'm not going through the derivation, but again, it's a good exercise in derivatives to try to, you know, a good exercise in algebra to try and compute that minimum explicitly. And so prox SGD for lasso, what it does is it takes a gradient descent step, or a stochastic gradient descent step, and then applies the prox operator, which means separately for each component of w, you move it a little bit towards 0 and have it stick there instead of crossing. And that works quite well in practice. It can be a very fast algorithm for solving a lasso. Okay, so there's a couple more questions on Piazza about how to interpret a precision matrix. So specifically, if we're talking about interpreting a precision by inverting it and interpreting the covariance, The question is, what does a covariance entry of 1 mean? And so, unfortunately, covariance entry of 1 can't be interpreted on its own. So we have a covariance matrix which looks like this, and we have, let's say, a variable x in one row and column, and a variable y in another row in the corresponding column. And so there'll be 4 entries that matter. Sorry, let's, we'll have this entry, this entry, this entry, and this entry, right? So a square, a 2 by 2 square submatrix, right? The xy entry, the xx entry, the yy entry, and the yx entry. And by symmetry, those two have to be equal to each other, right? And the question is, what does an entry of 1 in that box mean? And it depends on what the entries in these 2 boxes mean. So if x and y are each scaled to have variance 1, so if there's a 1 in all of these boxes, then a change of 1 in x will mean a change of 1 in y. And likewise, a change of 1 in y will mean a change of 1 in x. More generally, from this, you can figure out what an entry of 1 means in general, right? So if these are some other value, you'll scale x by its standard deviation to make it have a standard deviation of 1. That will wind up scaling this entry down from 1 a bit. Same thing, you'll scale y to have a standard deviation of 1. That'll scale this entry a bit as well. And then you'll say, since these entries are 1, this entry means how much does x change if you change y, right, on average. All right. So that's the answer to that one. So let's see, can the non-smooth term be infinite? Yes, it can be infinite. ProxSGD is designed for the case where the non-smooth term is convex. So that means it can only be plus infinity. The only convex function which is ever minus infinity. There's not much point in having it be minus infinity, because if you have it be minus infinity, any point that is in the region where it's minus infinity is going to have loss minus infinity, and so you'll just go there and be done. So let's say that it's finite in some region and plus infinity outside that region. So yes, having a loss function that's infinite is one thing that we can handle. It also asks whether you can have inflection points, and the answer is yes, right? So this kind of inflection point is also a good example of a valid non-smooth loss function. All right. So it looks like you know what, I'm just going to delete the self video for today because it seems like it is freezing all of the time. So goodbye me. There we go. So now hopefully that makes everything work a lot better, and you guys, the picture of me doesn't add a whole lot to the lecture. All right, I think that's the end of the questions on Piazza. So let's go back to our notes. So we just showed how to do lasso with proximal SGD. Not much more to say about that, except that it's a fairly simple algorithm to implement, and so it's a nice one. All right, so now we're going to take a detour through playing games, zero-sum games. And it's not immediately obvious why we would want to do that, but trust me, it's going to be relevant later. So in order to, so what do I mean by a game? I mean by a game there are two players, which we'll call W and alpha, and we have an objective function L that depends on both W and alpha. And it can still be a sum of terms where each term depends on both W and alpha. And so in order to solve a game like that, it turns out that stochastic gradient descent still works, except that the alpha player, because he's trying to maximize, should be doing stochastic gradient ascent instead of descent. We're just going to say SGD anyway, just with the understanding that the maximizing player is trying to go up and the minimizing player is trying to go down. And so what does the stochastic gradient descent update look like? In parallel, you want to update W by subtracting a multiple of the gradient, and update alpha by adding a multiple of the gradient. And you can have, I used the convention here of factoring t out of the learning rate, but you can also, as with SGD, use the convention that t is just included in the learning rate. So this factor of t might be present or absent. It's just a convention. All right. And so you can add regularizers as well. A regularizer is going to be separate for each player, and by regularizer I mean an L0 term. So L0 of W and minus L0 prime of alpha. You could have different regularizers for W and alpha. And so you can run SGD and it works. So it'll solve games as well as minimization problems. However, the statement "it works" is a little bit more subtle. And to see why it needs to be more subtle, imagine learning to play rock, paper, scissors. So in rock, paper, scissors, you have each player is picking a probability distribution over rock, paper, and scissors. So you could always play rock, always play paper, always play scissors, or you could do any randomization over those. And so you have your feasible region for each player is the simplex of probability distributions in on 3 elements. So it's basically a triangle. If you want to do well in this game, you can't necessarily play a deterministic strategy, right? Like you can't always play rock, because if you always play rock, your opponent's always going to play paper and you'll always lose. So in order to succeed, you're going to have to use randomization. And so the convergence guarantee for SGD in games actually includes randomization in the guarantee. So what does it say? It says that if we look back over all of our iterations and look at the W value that we had at the end of each one of those iterations, and we select one of those W values at random. And then the same thing for the alpha player, separately randomize over all of our iterations, pick the alpha value from the end of that iteration, and use that alpha. So that's going to give you a distribution over W for the W player, and a distribution over alpha for the alpha player. And if you do that kind of randomization, SGD guarantees that you will in fact converge to an equilibrium, meaning a point where, given the play of the alpha player, the W is at a local minimum, and given the play of the W player, the alpha player is at a local maximum. So just a caveat, you shouldn't expect SGD to necessarily in every game converge to a single point, although sometimes it does. And if it doesn't, it's going to wander around among multiple points, and you're going to need to effectively randomize among those points in order to see the benefit of the convergence of SGD. All right, so that's playing games. The message is basically SGD works for playing games as well. And now we get to see why we cared about that. So for let's see. So we're going to describe a technique which is kind of cool called Lagrange multipliers. And Lagrange multipliers are for helping us solve optimization problems with complicated constraints, at least more complicated than the sorts of constraints that projected SGD or prox SGD can handle. And so what we're going to do is we're going to start from a minimization problem, and then we'll invent a separate player, a second player, whose job is to enforce the constraints. So let's see how that works. So here is a minimization problem, kind of a very simple minimization problem, but a minimization problem nonetheless. So we're going to try and minimize w plus 2 squared, so that would have a minimum at minus 2. But we're going to have a constraint that w has to be bigger than or equal to minus 1, so you have to be in the unshaded area over here. Right? So the constrained minimum is here at minus 1 because the constraint prevents you from getting all the way to the true minimum. All right, so now let's suppose that we have a game that looks like this. Minimize over w, maximize over alpha, the same objective, w plus 2 squared, but now we've dropped the constraints on w and replaced it by this somewhat weird-looking product, minus alpha times w plus 1. And now we're going to constrain alpha to be bigger than or equal to 0. All right, so what's going to happen? First, let's suppose that the w player chooses something like minus 2, right, which the w player wants to do because that's where the minimum of her objective function is. So if w is minus 2, w plus 1 is minus 1, negative sign means plus 1, and so you're going to want to make alpha as big as possible, right? And since alpha is only constrained to be non-negative, you can make alpha equal to plus infinity, or I mean, you can't actually make it equal to plus infinity, but you can just, make it plus a billion or plus a trillion. And then the w player is going to be really, really, really unhappy, right? So on the other hand, suppose that you set w to be something over on this side. Let's say you set w to 0. Then w plus 1 is 1, negate that, minus 1. And alpha will have a negative coefficient, so you'll want to make alpha as small as possible. The smallest you can make alpha is 0. And so this whole term is going to drop out. And then if you set w, for completeness, if you set w equal to minus 1, then this is 0, and you don't care what, this term drops out, and you don't care how you set alpha. So to summarize, if the w player plays over on the wrong side of the constraints, the w player will be very, very unhappy. The alpha, she's trying to minimize, and the alpha player will be able to push the value of the objective function up really, really positive. So the w player won't play over here. The w player will be incentivized not to violate the constraint. If the w player plays on the correct side of the constraint, then that term drops out of the objective function. The alpha player is incentivized to play 0, and that term vanishes, and we just want to have w minimize that. So we've effectively made a new player who enforces the constraint that we had in the original game. So that's kind of cool. So then if we can solve this new game, which we can do with stochastic gradient descent, then we've solved the original constrained minimization problem. And this new variable alpha is called a Lagrange multiplier, after the mathematician named Lagrange who invented this idea. And it lets us get rid of constraints on our optimization variable w and replace them with another player, this alpha player, who basically plays in a way that enforces the constraints. So we did this for one inequality constraint, but we can do it for multiple ones. It's basically, if you have aj.w is greater than or equal to bj, which we'll summarize as a times w greater than or equal to b. So A is a matrix where the jth row is aj, B is a vector where the jth element is aj, and greater than or equal to is interpreted component-wise. And so if you have something like this, you basically just do the exact same thing over and over again, right? So for each one of our we introduce a Lagrange multiplier for each one of our inequality constraints separately. And what that looks like then is you have a vector of Lagrange multipliers alpha, and you add alpha transpose times the difference between the two sides of our inequality constraints. You add that to our objective, and you constrain alpha to be non-negative component-wise. And if you just go through the same reasoning, you get the same result, that the only way W can get a finite objective value, or the only way W can, limit how high the objective value goes, is to play in a way that satisfies the constraints. And if the W player does that, then the alpha player will be incentivized to set all of Lagrange multipliers to 0, and that term will drop out of the objective. Now, we've replaced our inequality constraints, AW bigger than or equal to B, with another player. And that other player, however, has some inequality constraints, has to play a non-negative vector. And so you might think that that's no progress at all, but sort of intuitively you can see that the non-negativity constraint is simpler than the arbitrary set of linear inequality constraints. And that difference is enough to get an efficient algorithm. I should point out as well that we only showed how to implement greater than or equal to constraints, but you can do less than or equal to by just, if you have a less than or equal to constraint, you negate it and you get a greater than or equal to constraint. Same thing works for equality constraints. It's the exact same thing. You add alpha transpose times the difference between the left and right hand sides of constraints to our objective. But the difference is that now alpha can be positive or negative. It's unconstrained. And if you go through the reasoning, the same reasoning applies. If the jth constraint is violated in the positive direction, then the alpha player will send alpha j towards plus infinity. If it's violated in the negative direction, the alpha player will send alpha j towards minus infinity. And if the jth constraint is satisfied, it's the coefficient of alpha j is 0, and that term drops out. And so the W player will want to play so that AW equals B, and that product will vanish. And you can mix the two, right? You can have inequality constraints by having non-negative Lagrange multipliers in the same problem as equality constraints that have unconstrained Lagrange multipliers. It works for nonlinear constraints too. Of course, you're only guaranteed to get to a local optimum instead of a global one, but this figure is maybe helpful for interpreting it, right? So we have our loss function, which is this sort of copper-colored contours. We have our constraint, which is this brightly colored line, curved line. And at a given point here, this is a local optimum because the gradient of the orange part, which is indicated by this vector here, is orthogonal to the constraint. And so what winds up happening is that there'll be I mean, this is sort of a geometric picture of what happens when you get at a local optimum with Lagrange multiplier. So we've got our new problem with Lagrange multipliers. We have our original loss function. We've got a bunch of Lagrange multiplier terms that enforce constraints, and then alpha has some constraints on its own, but it's a simple set of constraints. It's only non-negative. And the reason that that helps is that now we can use projected SGD on this new problem, because it's easy to project on the constraint alpha j bigger than or equal to 0. You just set alpha j to 0 if it was negative and leave it alone if it was positive. So you run stochastic gradient descent on that, right? And and it just works. You wind up solving this game, which is equivalent to solving the original constrained optimization problem. And so we have to run SGD, we have to split it up into terms. So L is already split up into terms, and maybe the conceptually easiest way to think about it is that you divide this into t pieces and include each one of them with one of the terms of the original loss function. You can do fancier things, but you know, what I just said is maybe the simplest way to think about it. And so to run SGD, you'll randomly sample a mini batch of terms. So that will be, you know, capital B terms from L of W plus B over T times the times this Lagrange multiplier term, and compute the gradient of that mini batch with respect to alpha and with respect to W, and update both alpha and W, and then project alpha back onto the non-negative orthant. All right, so we've talked about four different algorithms here, right? Plain SGD, projected SGD, proximal SGD, and Lagrange multipliers. And Lagrange multipliers, you can use any optimization you want, but projected SGD is a perfectly good one for that purpose. So what are the relative advantages and disadvantages of each of these algorithms? Basically, projected and prox SGD are very similar. They can both handle sort of simple-ish constraints. In particular, you have to be able to compute the projection or the prox function efficiently. But they satisfy their constraints exactly at the end of every step, right? Like when you project onto a constraint, by definition, you get a point that satisfies that constraint. On the other hand, Lagrange multipliers can handle much more complicated constraints. They can handle, for example, arbitrary linear equalities and inequalities. And so, you know, you don't have to worry as much about the existence of an efficient projection algorithm. However, because we're using SGD and dropping those constraints, we're going to wind up effectively satisfying the constraints only in the limit after you've been running SGD for a while. And so that could be inconvenient if you want, for example, a hard sparse vector W, or if some of our loss terms only make sense to evaluate for non-negative W, or you know, some other reason like that. So basically you have you know, the advantage of Lagrange multipliers is that they can handle a much wider range of constraints. The disadvantage is that they're more complicated to implement and that they have this only in the limit way of satisfying the constraints. So this seems like a good place to leave off. Our last class of the mini is this coming Monday, and then we'll have an exam on Wednesday. The exam, if you were in Mini 1, the way the exam is going to work is going to be very similar to that. In particular, we're going to release at the beginning of class period. We'll design it so that it should be possible to finish within the class period, at least if you're very familiar with the material, but we'll give you until later in the day to submit in order to account for possible technical problems with the submission. Yeah, so I think that's a good place to stop, and I'll